nanotechnology in 5G and beyond, enhancing communication infrastructure. How can nanotechnology revolutionize communication networks by addressing the challenges of miniaturization, signal integrity, and energy efficiency in 5G and future wireless systems, even as they push the limits of traditional materials and design paradigms? Modern communication infrastructure is entering a new era defined by the need for ever higher data rates, lower latencies, and more efficient energy use. The promise of 5G and the visions for 6G and beyond hinge on a radical transformation of network elements, from antenna systems to integrated circuits. Classical approaches to circuit design and material science can only take us so far when confronted with the stringent demands of next-generation communication. Enter nanotechnology. By manipulating matter at the nanoscale, researchers and engineers are uncovering new ways to overcome the limitations of traditional semiconductor and photonic technologies. So far, so good, until we examine the intricate challenges presented by the evolution of wireless communications. The nanotechnology and 5G and beyond paradigm emerges when the precision of nanoscale engineering collides with the complex requirements of modern network infrastructures. Under ideal conditions, if every component of a communication system could be designed with atomic-level accuracy, traditional materials might suffice. However, as the move toward higher frequencies and densely packed device architectures intensifies, classical bulk materials and conventional design philosophies rapidly approach their performance ceilings. Nanomaterials and nanoscale fabrication technologies offer a new toolkit for transcending these limitations. One striking example is found in the development of nanoscale antennas and metamaterials. In these systems, the periodic arrangement of nanostructures can manipulate electromagnetic waves in ways that defy the predictions of classical optics and radio frequency design. Much like photonic crystals create band gaps for specific light frequencies, nanostructured metamaterials can guide, bend, or even concentrate radio waves, opening up avenues for enhanced signal control and improved antenna performance. This phenomenon allows for the miniaturization of components without sacrificing or even enhancing functionality, a critical advantage as device footprints shrink and operating frequencies climb into the millimeter wave and terahertz domains. At even smaller scales, the materials themselves demonstrate properties that dramatically differ from their bulk counterparts. For instance, graphene and carbon nanotubes exhibit exceptional electron mobility, thermal conductivity, and mechanical strength. When integrated into transistor channels or interconnects within radio frequency integrated circuits, these materials can significantly enhance performance and reduce power consumption. This is particularly crucial for ensuring that the high-speed, low-latency demands of 5G networks and later generations are met without incurring prohibitive thermal or energy costs. And then there is the question of integration and fabrication. Nanotechnology is not merely about discovering new materials. It also encompasses innovative manufacturing techniques such as atomic layer deposition, electron beam lithography, and self-assembly methods. These techniques allow for the construction of complex three-dimensional architectures that were once the realm of science fiction. They facilitate the integration of diverse nanomaterials into hybrid systems, where electronic, photonic, and acoustic functionalities converge to create devices that are far more capable than the sum of their parts. Even in controlled laboratory settings where nano-fabrication processes are fine-tuned to near perfection, the reality of scaling these techniques to industrial volumes introduces a host of new challenges. Minor variations in nanostructure geometry or alignment can have outsized impacts on device performance, similar to how small perturbations in a fluid can lead to a turbulent cascade. However, these challenges are being actively addressed through advanced simulation techniques, feedback-controlled fabrication, and adaptive design algorithms that help ensure consistency and reliability across mass-produced systems. So what is truly happening? The revolutionary potential of nanotechnology and communication infrastructure does not undermine the fundamental laws of physics. Maxwell's equations and quantum mechanics remain the bedrock of our understanding. Instead, it highlights the limitations of traditional design models that treat materials as homogeneous and devices as two-dimensional constructs. The transformative capability of nanotechnologies stems from their ability to harness quantum effects, nonlinear interactions, and geometric intricacies at a scale where the collective behavior of atoms and electrons can be engineered to achieve unprecedented performance enhancements. In essence, by embracing the complexities of nanoscale phenomena, engineers are crafting communication systems that effectively bypass the conventional barriers imposed by bulk materials and classical device architecture. Nanotechnology in 5G and beyond serves as a powerful reminder that as we push the limits of communication technologies, our tools and models must evolve in tandem. It challenges conventional wisdom and compels us to adopt a richer, more nuanced understanding of how matter and energy interact at the nanoscale. This frontier not only promises to revolutionize wireless networks by delivering higher speeds, more efficient energy use, and enhanced signal control, but it also opens up a world of innovative applications and system architectures that will define the future of global connectivity. Nanotechnology leverages the design and manipulation of materials at the nanoscale to transform communication infrastructure. It enables components with enhanced electromagnetic properties, reduced size, and improved energy efficiency, all crucial for 5G and future networks. This technology underpins advances in antenna design, signal processing, and overall network performance. Carbon nanotube-based antennas can outperform traditional metal antennas by offering greater bandwidth and efficiency in compact formats. It is like upgrading from a bulky satellite dish to a finely tuned miniature receiver that captures more signal with less interference. Nanomaterials such as graphene, quantum dots, and carbon nanotubes exhibit exceptional electrical, mechanical, and thermal properties. Their unique characteristics enable faster signal propagation and miniaturization of critical communication components. These materials pave the way for designing circuits and antennas that operate efficiently at high frequencies. Graphene is being used to create ultra-fast transistors that can handle the high data rates required in 5G networks. It is like replacing standard building blocks with super lightweight, super strong components to construct a more agile and responsive structure. At the nanoscale, materials demonstrate quantum confinement effects and tunable conductivity that are vital for advanced signal processing. These properties allow for the modulation and manipulation of electromagnetic waves with remarkable precision. As a result, nanoscale devices can transmit and receive signals with reduced loss and greater clarity, even at very high frequencies. Quantum dot-based photodetectors are capable of converting light signals into electrical signals with high sensitivity, essential for high-speed data transfer. It is like having a microscopic orchestra where each instrument plays in perfect harmony, resulting in a flawless performance that traditional setups cannot match. Nanostructured antennas exhibit dramatically improved performance by leveraging their high surface-to-volume ratio and unique electrical properties. Their engineered geometries allow for effective radiation and reception of high-frequency signals, essential in 5G communications. Moreover, these antennas can be seamlessly integrated into portable devices, providing enhanced connectivity without compromising on size. Carbon nanotube antennas integrated into smartphones demonstrate higher gain and broader bandwidth than their conventional counterparts. It is like redesigning a traditional antenna into a finely tuned musical instrument where every string contributes to a richer and more precise sound. Nanotechnology facilitates precise control over the interactions between electromagnetic waves and nanomaterials, essential for effective frequency management. Advanced nanostructures can be engineered to filter, direct, or enhance particular frequencies while suppressing unwanted noise. This selective frequency control supports the simultaneous transmission of multiple data streams with minimal interference. Metamaterials with embedded nanostructures are developed to create frequency-selective surfaces that optimize signal clarity in dense communication environments. It is like having a set of microscopic traffic lights that direct the flow of vehicles so that each lane frequency band operates smoothly without collisions. State-of-the-art nano-fabrication techniques enable the production of highly precise and scalable nanostructured components for communication systems. Methods such as electron beam lithography, self-assembly, and 3D nanoprinting allow the realization of complex designs at a scale suitable for industrial applications. These advances not only boost performance, but also drive down the production cost for next-generation devices. Advanced lithography, is used to pattern graphene and other nanomaterials into intricate antenna arrays that meet the stringent demands of 5G technology. It is like using an ultra-high principal action printer to produce intricate circuit diagrams, ensuring every minute detail contributes to an impeccable overall performance. Nanotechnology enables significant miniaturization of communication components, leading to more compact and integrated devices. The reduced size of these components permits their incorporation into a broader range of platforms, from wearables to IoT sensors. Consequently, the integration of nanotechnology in device manufacturing promotes a more interconnected and high-performing communication infrastructure. Miniaturized nanoscale transistors and antennas have led to the development of smart devices that can easily operate within the dense networks of 5G and future communications systems. It is like switching from large, clunky mechanical parts to precision-engineered microcomponents that seamlessly fit together in a complex, efficient machine. The implementation of nanotechnology in communication infrastructure faces challenges such as scalability, manufacturing consistency, and integration with existing systems. Ensuring reliable performance of nanoscale devices over a wide range of operating conditions is a significant technical hurdle. These challenges drive continuous research into new materials, fabrication methods, and testing standards to make nanotechnology a standard part of communication systems. Maintaining uniformity and stability in large-scale production of graphene-based components remains a critical focus in industry research. It is like transitioning from handcrafted artisan tools to mass-manufactured ones, where consistency and durability must be rigorously maintained across all units. Ongoing research in nanotechnology promises to revolutionize communication infrastructure not only for 5G, but also for the emerging 6G and beyond. Future developments will likely see the integration of adaptive nanomaterials, self-healing circuits, and quantum communication elements that significantly enhance network performance. These breakthroughs could lead to fully integrated, smart communication ecosystems with unprecedented speed, reliability, and energy efficiency. Researchers are exploring self-assembling nanomaterials that could dynamically adjust their properties to optimize network performance in real time. It is like evolving from static road networks to dynamic, self-regulating smart highways that adapt to traffic conditions instantly, ensuring smooth and efficient travel for all data packets.